I want to close out the week by changing gears a little bit and talking about the procedure of doing scientific experiments and interpreting the results of scientific studies, and then the process of science as a whole, as an industry, as it were. Because there's a few subtle differences that I think are important for your ability to interpret scientific research in the future, and more pertinent to this class, your ability to do the equipment proposal project and some of the scientific article analyses that are coming up in future weeks. So suppose you have some experimental question. Maybe you're interested in high intensity interval training versus low intensity exercise, and let's just call it low intensity. And your outcome of interest is maybe, body composition. You're interested in, is high intensity interval training better than low intensity interval or low intensity continuous training for body fat percentage? So you probably know how you might go about this. Get some big group of people, maybe you get 100 people, and you randomly assign some of them to the high intensity interval group, some of them to the low intensity interval group, low intensity exercise group, and before and after the protocol, you measure their body fat. So maybe we make a little graph, and we have pre, post. So I don't know, maybe this is 16 weeks, 16-week training program, pre, post, and presumably maybe you did a study on people who are on average 20-ish% body fat. Here's the one group, here's the other group. Presumably they'd be pretty similar beforehand, right? Because you randomly assigned them. That's kind of the key to these randomized experiments. And maybe the low intensity interval group drops a little bit of body fat, but the high intensity exercise group, maybe they decrease like this. So you might conclude, oh, this is better than this for this outcome that I care about. Now, when you see these kinds of things reported in the scientific literature, there's a number and a uncertainty estimate that is regarded as the primary finding, which is how different were these two groups at the post, right? So of course, nobody cares about how different they were at the baseline because they shouldn't have been different at all. You just randomly assign them. And nobody really cares how much each individual group changed within the program because that's less interesting than what was the difference between this and this. That was the whole point of the study. You would do things differently if all you cared about was how much body fat do you lose from any type of exercise. So what we care about is how big is this difference? And generally, the way you'll see that reported is some estimate plus or minus some error. Generally, this error is reported as something called a confidence interval, 95% confidence interval. And people work themselves into all sorts of fits discussing how precisely you should interpret it. But let me recommend interpreting this way. Let me make a one-dimensional plot, and I'm just going to plot change. Are you okay? Hopefully you're okay with me using delta for change in percent body fat. And this is between groups. Right, so low intensity versus high intensity. And what we want is some, assuming we think high intensity exercise is better, maybe this is, maybe they lose 5% more body fat than the low intensity group. Oops. That's better. So we would have some point estimate right here at -5. But there's some uncertainty associated with that, right? Because there's random variation in how people respond to exercise, random variation in things you couldn't control for in the experiment. So you would expect some kind of like error bar like this. There's something else that you will see quite commonly, which is called a p-value. And I'd rather not get into the exact interpretation of this, but people get very excited if their p-value is less than 0.05. And you can think of this as like a surprise factor. So assuming there was no difference in your data, how surprised should you be? Or in other words, how common would it be to observe the results you observed or something more extreme if in truth there really was no difference? I find p-values a little bit tricky to interpret. I would rather recommend to you interpreting the confidence interval. So let's say this confidence interval goes from -9% to -1%. And in the middle, right, our best estimate of the effect of this exercise program is compared to low intensity exercise, this interval program decreased body fat by 5%. But the data we have and the modeling assumptions that we used when we analyzed these data mean that we're at a 95% confidence level. Our data and our models are compatible with between -1 and -9% change in body fat. So this is good, and people get excited when their confidence interval does not cross 0, meaning no effect. Maybe you did a different study. Maybe you did a study on, I don't know, weightlifting versus endurance training. And you found the weightlifting group lost -3% more body fat, but your confidence interval went from +1% to negative, let's see, what would a reasonable number be there? -7%. So our best estimate is the weightlifting was better, but we're not really sure because our uncertainty includes both positive and negative numbers. So that's how people tend to present their results, and I recommend you consider this level of this confidence interval as a level of a range of plausible values. So this intervention might increase your body fat by 1%. It might decrease it by -7%. Our best estimate is -3, but this is the range of values that are compatible with the study we did. Now, that's how you would think about one study. So for example, the article analysis for this week likely presents estimates of how much bone mass the astronauts lost during their 6 months in space. And maybe they present that as some percentage of bone mass with some uncertainty, some confidence interval around it. The piece that I really want to introduce to you, and this is kind of like a new thing for how we do science in the 21st century, is how do you think about aggregating the results of many different studies? One of the big mistakes that I see people make when they read scientific literature on some topic they care about, such as high-intensity interval training versus low-intensity exercise, is they find one study and they look at it and they say, well, okay, this study found a significant result of -5% in body fat, therefore high-intensity interval training is better. There's a modern approach to this problem, which is, suppose you went into the scientific literature and you gathered up all of the studies that anybody has ever done on the topic that you care about. This is an approach called a systematic review. And when you pool all the results of those studies, it becomes something we call meta-analysis. And these are great because you can pool results from many different studies and get a very, very, very precise estimate of whatever it is you care about. Generally, in these meta-analysis studies, you see plots like this. They're called a forest plot because you have these little trees of uncertainty. And each of these is the same little point estimate and an uncertainty bound that I introduced right here. And the idea is you just stack them up and then you take a weighted average of all of them. So this figure I'm showing you right now is actually from something I was looking at when preparing the materials for last week. Maybe you remember we were talking about exercises to improve the mechanical properties of tendons. So suppose you have somebody and you want to make their tendons stronger. You might wonder, should you do high intensity exercise versus low intensity exercise? And I told you, and in the class notes I have, high intensity exercise is better for strengthening tendons. How do I know that? I went to this systematic review which compared high intensity exercise for tendon strength with low intensity. So they took a bunch of studies that used high intensity strength, they pooled all those results together, and they got this final estimate, which is positive, meaning exercise makes the tendon stronger. They pooled all the low intensity studies together, and they got this estimate, which is almost exactly 0. So low intensity exercise does not seem to change the mechanical properties of tendons at all. Something that's really beneficial about these meta-analyses is that you may notice in this forest plot, many of the individual studies did not find results that we would deem statistically significant. So for example, this study found an effect for high intensity exercise making your tendon stronger, but maybe they didn't have that many subjects. Their uncertainty bounds included both detrimental effects and positive effects. That was also the case for this study and for this study. Now this was a statistically significant study because the uncertainty bands did not include 0. But what's great about these meta-analyses is you can add up all these small little studies and then get a pooled result that's very, very strong, meaning you can be very confident in it. One of the frustrating things about exercise science is that quite often you'll see studies with 10 subjects, 20 subjects, really small numbers, and it's hard to be really confident in the results of those studies. But the great thing about systematic review, and especially this meta-analysis strategy, when you pool all those results together, is even if each of these individual studies only had 10 people in them, well, there's 27 of them. So now you've got 270 people, and that's actually a lot. So if you have a question, especially about something that's commonly researched, like weightlifting, exercise for blood glucose levels or blood pressure, weight loss, plyometric training, there's likely a meta-analysis on it. So you can go onto a search engine like Google Scholar and search whatever topic you are interested in, plus meta-analysis or plus systematic review. Now, I do want to close by saying that these are not the end-all be-all of scientific research for 2 reasons. One of them is that you do have to have some criteria about which studies you include and exclude. And generally, we try and be as, well, as the name would suggest, as systematic about that as possible. But the other more subtle point is sometimes you have really unique circumstances that you cannot just do a bunch of studies on. So for example, the study that we're reading for this week, a study of 17 astronauts on the International Space Station, there's not going to be 27 different studies of them. So sometimes when you have really unique circumstances, really unique athletes, very rare medical conditions, you really do have to look at individual studies. So I hope you found this helpful in your quest to learn more about interpreting the results of scientific research.